Hi everyone, I'm Junhua. Today I will work with Harry to talk about how we integrate MLFlow and implement the distributed training framework into our Jupyter-based paper notebooks, and how it will affect the machine learning and the data science experience. Here is the agenda. Firstly, I will talk about distributed training and cover some topics like what is distributed training and what kind of problem it's trying to solve. And also, I will talk about the implementation. Then Harry will talk about MLFlow, and he will cover some topics like what is MLFlow and how it's integrated into the notebooks and what's the user experience. Then he will do some demo. Here is some brief self-introduction of ourselves. I'm Junhua Zhao. I'm a software engineer and a big data machine learning platform engineer at PayPal. And I am experienced in building high scalability and availability distributed system. I'm also a professional in building machine learning platform. Harry is also a software engineer at PayPal. Currently, he is in AI and ML platform. He have 10 years of building. He have 10 years of experience in building the distributed and scalable application. Let me give you some background to start the topic. In PayPal, we have an internal Jupyter Notebook environment called the PayPal Notebook. It helps the data scientist to do data processing, data analysis, and model training. In a data scientist day-to-day work, they need to do a lot of different tasks to develop a model. We have built or integrated different tools to help them. Today we will talk about how we implement Today we will talk about the distributed training framework that we have built and explain what problem it will solve and how it helps some tasks like running the model training and makes it faster. And also it will help the hyperparameter tuning. Also, we will talk about how PayPal integrate with MLFlow and how the data scientist can use it to do something like to help them to track the progress and evaluate the performance among different experiments. Now, let me firstly talk about distributed training. Okay, let me explain what is distributed training and why data scientists need to use it. In this chart, it shows a trend in the AI industry. We are getting more and more data, and the models are getting more and more complex. It is important to make sure that the speed of training is still fast, in spite of the huge amount of data and the increasing of model complexity. And we want to make sure that the data scientists can still develop and iterate their models in a fast pace. And this model training cycle can still move faster. Distributed training can help us to deal with this challenge. In distributed training, the workload to train a model is split up and shared among different devices. For example, you can split the model into different layers and put it into different devices to do the training, which is called model parallelism. Or you can split the data and each device train the model on different part of the data, which is called data parallelism. Because these devices run in parallel, the speed of training is faster. Also, there was a GPU resource utilization problem when we implemented the GPU-based PayPal notebook. By implementing the distributed training framework, this problem will be resolved automatically. I will explain it in details in the following slides. Here is the previous architecture in PayPal notebooks. You can see that we have deployed the Jupyter server kernel gateway in the Kubernetes cluster in some CPU-based pod. After the user login, he started the server. One Jupyter server will be created and dispatched to the user. And then the user may create some new kernel, which requires GPU. For example, here he is trying to create a TensorFlow kernel with GPU resource. And the kernel gateway will allocate the GPU resource from the Kubernetes while the kernel is creating. A pod YAML may be created like this. You can see it's trying to allocate several GPU resources from the cluster. And the kernel, the TensorFlow kernel, will run inside this pod. Here is a typical model training notebook. You can see it's trying to load some data. It's trying to analyze the data, and the user may spend some time to analyze the result and also editing the code. So you can see here in these steps, the GPU resource is not used except the model training, but still this GPU is occupied because the kernel is running inside it. It's a huge waste of resource. Here is another diagram shows how the system behaves. The GPU is occupied. Even the user is just editing the code, the notebook code. So over the time, this is what will happen. All the GPU nodes will be occupied, even though not many are actually running the training job. Because the nature of the distributed training framework, training tasks need to be run remotely to the Python kernel. We can just create the kernel in a CPU pod instead of a GPU pod, and the distributed training framework will allocate the GPU resource only after the actual training have started. This resource utilization problem will be resolved automatically. Here is the new system after using the distributed training. You can see that when the user is editing the code or downloading or processing the data, the kernel is running on a CPU pod. Only after the actual training starts, the GPU resource will be allocated on demand to the user. Okay, we already know what is distributed training and what problem it can resolve. And we do want to apply distributed training in our notebook. Here is a list of targets and the problems we want to achieve or address when we applying it. So firstly, we want to have a faster training speed. And also we want to have a better GPU resource utilization. And also a seamless user experience. So when the user runs the distributed training on his model, it should be as easy as running normal training notebooks. And also we want to abstract the underlying frameworks so that it will be easy to extend to some other new frameworks. And also it makes the migration easy if we want to migrate to some new deployment environment. And also we want to provide the out-of-box hyperparameter tuning feature. So we have compared some open source distributed training framework and try to pick up some solution that can fit our requirement. Here is the solution we have chosen for our requirement. Firstly, we have chosen Harvard as the underlying distributed training framework because in PayPal, we have lots of data scientists and they use different training frameworks. Harvard can support most of them. And also we have chosen Kubernetes with MPI operator because it provides a good abstract on the GPU resource allocation and the job scheduling logics. And also it makes it decoupled from the underlying deployment environment. It makes our system very easy to migrate. And also we have developed the shared workspace. It provides a seamless experience to the user. The user can just upload the data or the Python dependency library or the training scripts into the workspace, and it will automatically be accessible by all the training GPU pods. And also we have chosen the hyperopt for the hyperparameter tuning. Here is one example showing how this solution works. Firstly, you need to create a training script. This training script does the actual training, and it needs to use the Harvard internally to do the parameter updating. Secondly, you need to create a training launcher notebook, and you can download the data or even process data in it because it will run in it will be executed in a CPU pod. And inside this notebook, you need to invoke the PayPal distributed training supporting library to start the actual training job. This PayPal distributed training supporting library will create a MPI job internally, and it will be created in the Kubernetes cluster. And there's an MPI operator will watch for those jobs and allocate the GPU resource based on these jobs. In each GPU pod, the training.py will be executed, and these pods will communicate each other for the parameter updating by using the Harvard library. So Harvard will update the model parameters by using all-radius algorithm, which is the main part of the distributed training. This is a new system architecture. You can see that the Jupyter IPython kernel will be created in this CPU pod. And when you do the data processing, data loading, everything will be executed in this CPU pod-based kernel. So only after the actual training started, the underlying infrastructure will allocate the GPU resource for you and it does a distributed training for you. So that's the main difference. Here is a detailed design and a plan for our distributed training supporting library. You can see more details in this diagram, something like monitoring and also the log retrieving and the optimization. Yeah. So let me do some demo to show you how it works. So you can see that I've already created this training.py, this Python file, which does the actual training. And this file is in the workspace. And also, I have created this train launcher. So after I execute this, you can download data or even process the data in this Jupyter notebook file, because it will be executed in the CPU node. Okay, now I will start to invoke this PayPal distributed training supporting library to submit the training job to the GPU. So now you can see I've already tried to run it, and supposedly we should already see the GPU pod being created. Yeah, it's already created. We can also tell the log from this cell. So you can see it's already warming up and start to run. So in this example, we have two nodes. And they will update the parameters. You can see it's either progress. Yeah, so the distributed training is working on this machine. Yeah, I think that's all. Thank you, everyone. Now, then hurry talk about MLFlow.
MLFlow. MLFlow is an open source platform for the machine learning lifecycle. In order to build a successful machine learning model, a data scientist has to go through a lot of phases. Building a model, training the model, comparing the performance of different experiment runs, and fine-tuning the parameters used in order to pick up the best performing model. Many of the data scientists track the params and metrics manually. And there is no single place to view different runs for an experiment. Params used for each runs, performance of the model, and output artifacts of the run. So if a data scientist who initially worked on version 1 of the model goes on vacation or leaves the company, it is very difficult for other data scientists to pick up his work and enhance the model. MLflow addresses most of this problem. There are other challenges like reproducing your own results, enabling others to reproduce pipelines, comparing results from other versions, moving models to production, redeploying and rolling out updated models adds more complexity to this problem. To address these challenges and accelerate model building and deployment process, AI/ML team in PayPal has built ML platforms to automate the end-to-end ML lifecycle. In this demo, I will walk through the integration of notebooks with MLflow. Now we have integrated MLflow with Jupyter Notebooks. First step is we created a dedicated MLflow instance for tracking different experiment and its run. Also, we have installed MLflow client library in our notebooks environment. From our notebooks environment, data scientists will be able to connect to this MLflow instance to log and track the experiments. We created a new notebooks extension for data scientists to quickly view the list of runs for an experiment, params used for each run, metrics captured for each run. Currently we have provided a provision to sort the experiment runs by the date in which the experiment was run. We also offered an integrated experience of using MLflow within the Jupyter Notebooks. We achieved this by adding a new tab in Jupyter Lab to view MLflow UI without having to hop between different tabs. MLflow UI is displayed as an iframe within the Jupyter Notebooks. So for security, even though we have a centralized MLflow server that will be used by different data scientists across PayPal. Using namespace concept, we display only the experiment that the logged in user has access to. So this is something we achieved using the namespace concept that is available in MLflow. And we have integrated with popular MLflow libraries like TensorFlow 2, H2O driverless AI, Keras, etc. And we have also leveraged the great features offered by the PayPal notebooks, like it has integration with Teradata, Hadoop, etc. And we have scheduling, GPU training, distributed training features. So all this we would be leveraging. So a data scientist should be able to access all the data needed to build a model and train the model. Jupyter Notebooks MLflow integration by creating an experiment using MNIST dataset. The objective of this experiment is to build a best performing model that correctly predicts the handwritten number from the MNIST dataset. Here I am creating an experiment called MNIST underscore Tony experiment with the namespace as TonyVo. Here, as you can see, I am connecting to this MLflow instance. This particular MLflow instance has lot of experiments. As you can see, it has lot of experiments, each created with different namespaces. But within the notebooks environment, we display only the experiment that the current logged in user has access to. I only experiment the user Tony Wu has access to will be displayed. So this is a new extension that we have created. This particular extension will list down all the experiment that the current logged in user has access to. And selecting an experiment will display all the runs for that particular experiment so far. Also, it displays the different params used and the different metrics that are logged into the MLflow. So this particular extension might come handy for data scientists. They can quickly change the params, run the experiment and refresh the screen to see how the model is performing. For example, let's say that I think I already ran this with top learning rate as 0.5, 0.4. Let me run this with the op learning rate as 0.6 and see how the model is performing. So these are all the parameters that are being logged into the MLflow. Here we are using the auto log features offered by TensorFlow and MLflow. So let this get completed. So now the experiment is completed, and if you refresh, you should be able to see a new run. Yeah, here we are seeing a new run, and the opt rate is 0.06. So which we just changed and ran. So this will come handy, and they should be able to see how the model is performing. Like when the learning rate is 0.06, the accuracy was around 0.90. If the learning rate was around 0.5, it was accuracy was around 0.93, which is better compared to the uplearning rate of 0.06. So this comes handy if the data scientist want to do more advanced features offered by MLflow. You can click on the experiment tab that we have introduced in Jupyter Lab to get a full-fledged MLflow experience. They should be able to compare different runs and view the performance graphically and download the artifacts as well. So here they should be able to compare the different runs and its performance. They should be able to change the loss percentage, compare it visually. And for each of the runs, all the artifacts are also logged to MLflow. Here they should be able to see that model summary, everything. And downloading the model artifacts is also possible.
Thank you, Harry, for sharing it. And thank you everyone for attending this conference. Hope you have a nice day.